In this video I'm going to cover the concept of matrix multiplication, that operation, how we perform that operation, and I guess first of all when we can perform that operation. So we said previously that we can add or subtract two matrices when they are of the same size. That's not necessarily the case for matrix multiplication. So we can describe two matrices as being conformable for multiplication if the number of columns of A equals the number of rows of B. And importantly, it means A times B in that order. So A times B will work if the number of columns of A equals the number of rows of B. So let's talk in a sort of slightly more specific sense. Well, we'll at least give these some values or some letters, and then we'll do some specific examples. So let's say we have matrix A is an M by N matrix, that's its size or order. And let's say B is an N by P matrix. Well, because the number of columns in A, which is the second number there, the N, is equal to the number of rows in B, the N being the first number, then we can say that this, works. I guess that's a maybe more colloquial way of saying it's conformable. So it works, and we can actually know that the matrix AB, this product that we get from doing that, we can know that it will have order or size M by P. So let's just sort of write out. So what we're doing is A times B and getting the resultant matrix AB. So let me write them here with their order. So A is M by N. We're multiplying that by N. N by P. And so first of all, if we look at the two inner numbers, they're the numbers that need to be the same, because they represent the columns of A and the rows of B. So as soon as they're the same, so if I look at those and they are equal, then that implies this is conformable for multiplication. Just write an abbreviation there for multiplication. But the thing then that tells us what the order of the product will be is the other two numbers. So the number of rows here will be the number of rows in the product, and the number of columns here will be the number of columns in the product. So this will be an M by P matrix. Alright, now what about the actual process of performing this? Well, in some ways we can actually think of this as like a series of dot products. So matrix multiplication can be thought of, or I suppose performed, as a series of dot products. And I guess if we keep using the matrices A and B, then it's a series of dot products of the rows of A with the columns of matrix B. So what does that look like? Well, let's go up the top here, so I've got a little bit of space, and let's define a couple of matrices. So I'll go here with a 3 by 2, so negative 2, let's make that negative 1, we'll make that 1 and 3, and this can be 2 and 4, and then we'll let B just be a 2 by 2. So if we're going to perform multiplication, I guess first of all we could just double check that these are conformable. So let me grab another color here. We wouldn't normally do this, but let's say we'll check if conformable conformable. And so if we're checking that they're conformable, we would just write their actual sort of size or dimension. So A is a 3 by 2 matrix, B is a 2 by 2, and so since these numbers here match, we know it's going to be conformable, and we also know that the resultant matrix will be a 3 by 2. Now notice there I'm not performing the operation, I'm just checking conformability. So that's A times B, it works, and the product matrix that I'll get will be a 3 by 2. Alright, so let's do this series of so-called dot products. So calculate the matrix AB. Well, AB is equal to, writing these two out beside each other, 3, 0, 2, negative 1. Okay, so a series of dot products between the rows of A and the columns of B. So I go, let's grab a highlighter here and say row 1 from here, take its dot product with column 1 there. So if I do that dot product, I'm going negative 2 times 3, which is negative 6, plus negative 1 times 2, which is plus negative 2. Alright, so that was the first one. That's the value I'm going to get there. Now let's maybe use some different colors here. So for the second one, let's go row 1 times column 2. So the dot product of row 1 with column 2. And that's going to get the value for the entry in row 1 and column 2, which is this one over here. So I'm multiplying row 1 in the first matrix by column 2 in the second one, and I'm getting the entry in row 1, column 2. So negative 2 times 0 is 0, plus negative 1 times negative 1 is 1. Now, going down to the second row, so in the second row, I'm going to take the dot product of row 2. Let me just do another one here. So row 2 there, with column 1 there. That'll give me the next entry. So 1 times 3 is 3, plus 3 times 2 is 6. And then row 2 with column 2, 1 times 0 is 0, and 3 times negative 1 is negative 3. And now I'm down to row 3. Its dot product with column 1, 2 times 3 is 6, plus 4 times 2 is 8. And then the dot product, let me do a highlighter just for this very last one. So now I'm down in row 3, its dot product with column 2. That's going to give me the entry in row 3, column 2. So 2 times 0 is 0, plus 4 times negative 1 is negative 4. So what do I get? Negative 6 minus 2 is negative 8. 0 plus 1 is 1. 3 plus 6 is 9. 0 minus 3 is negative 3. 6 and 8 is 14. And 0 minus 4 is negative 4. Alright, so that's how we perform matrix multiplication. Now, just before we finish up here, you might have been realizing or noting, and certainly if you haven't, you should do before we finish, note that this way of defining matrix multiplication means it is definitely not commutative. So, in this particular case, we can say BA does not exist. And the reason BA doesn't exist is that if we were multiplying matrix B by matrix A, we'd be trying to multiply a 2 by 2 times a 3 by 2, and those numbers there don't match, and so therefore this would not be conformable for multiplication. So BA does not exist in this case. It's not saying it will never exist in any case, but in this case it doesn't exist since it is not conformable. So straight away we can say that matrix multiplication is not commutative, but even in cases where both A times B and B times A do exist, we'll see that even then they won't in all cases give us the same result, and therefore we conclude that matrix multiplication is not commutative. So let's just make that statement. So matrix multiplication is not commutative, and hopefully you might recall that commutative, you might recall that commutative means that you can switch around the order of the... Now, that's not to say that A times B would never equal B times A for any matrices A and B, but because we can't say it's always true, therefore we have to say matrix multiplication is not commutative.